Hello. So today we're going to be building Spectra, which is a vision transformer, and I'm going to be showing you how to build vision transformers as simply as possible. I'm Kai. I've been an AI engineer since I was around 10 years old, leader of Agora now, and essentially I just implement models all day, create models. So I'm going to be showing you how to create vision transformers right now using PyTorch and Zeta. So here we're just importing some stuff, feed forward, multi-group to create attention, feed forward, stuff like that. Put some stuff here. So basically what we're doing here is just initializing some stuff, some critical variables. Just let Copilot do this. So here we're going to specify our attention. Let's see. Let's add a line arm. And that's pretty much it. Now let's add a feed forward. So here we're using multi-group to query attention. Multi-group to query attention is currently the best attention network in terms of speed and just general reliability. It's really fast. Yeah, so here we're going to set the multiplier to 4, and again we're going to use swish and the post-act layer norm. So layer norms again help with just general training stability. Without layer norms, this wouldn't really be very stable. So here we're going to initialize a layer norm, and here we're going to create the forward pass. Alright, so here we're going to normalize the input tensor. Again, we're going to create the skip. Then we're going to apply attention. I don't know what this is outputting. Let's see. Yeah, so 2 kV values. Yeah, okay. Is it ace casual? Yeah, okay. So ace casual. Nice. So then we're also going to add the skip. And then here now we're going to do skip 2. Now we'll do feed forward. And that's pretty much it. We could also do something like this. Just add a norm. This will just make it much better. Alright, now. So now we have a transformer block. Now it's time to actually make the model. Now this is where the image processing stuff comes in. So let's make a model called Spectra. Again, we're going to copy all of these parameters. but we're gonna add a couple things. So patch size is equal to 16. Image size is equal to 16. What else? Patch size is equal to 6. Number of classes. So how many classes you want it to output? Most times it's 1,000. Here are some other things like conditional variables and whatnot. So patch size, image size, number of classes. So the image size is usually 224. Number of classes is 1,000. And so now we need to patchify this. So let's upgrade Zeta. So pip install Zeta scale. And we should get the new version of Zeta. So let's keep building this out. So what we're going to do is here we're going to essentially patch the image. So we're going to initialize the layers first.
What do you mean?
I also forgot the def. So that's what else to do, Norm. So here we're going to initialize everything. So first patch image. This is very simple to use function from Zeta that we're using. Otherwise, this would normally take a lot of time. I'll also add the channels. Just almost 3. Channels are like the number of different channels inside the image. And we're gonna add this to 2. Gonna organize this code a little bit. So then after this, we're going to apply the transform blocks to the outputs, and then there's one last thing. There's the output heads that we need to apply, so we can norm this, and then the ViTs output head. So and that's pretty much it. Yeah, so that's how to make a vision transformer. You basically well, it's the same setup as a normal, transformer, except that the way you're processing the inputs, the images, is just different. You're patching them, you're taking them from, they're going to be of this shape. They're going to be a 4-dimensional tensor like this. So this is the first one is V channels, heights, and width. And more or less, like, the flow is kind of simple. It's image, patch, linear, flatten, transformer layers, outputs, classification. And that's kind of like a more or less like, this is a very simple implementation. Let's actually get into the debugging phase of this. Run a forward pass. I expect there to be some errors, but let's see. Don't expect anything to ever work. If you expect something to work, it's probably not gonna work. But that's good, because if you expect it to work, then you can take steps to fix it. But don't ever assume something will just naturally work. And if you do that, you'll never be surprised. This is a continuous process, and we have to be like constantly learning how to fix things. It's taking some time because my computer is old, but let's see. Let's see. Let's see, we need to reduce this tender. I see. There's a problem with the attention. Okay. We can just use another one. So dim, heads, quick on. And that should be it. Let's try that again. Come on. Let's get that output. Okay, so there's an input problem with this. Let's see if we can fix it. These are some pretty new features, patch, linear, flatten, and ViT output head that I was working on last night, so let's see. I see. So this is completely like unrelated to Spectra. This is like just some personal errors I made. Oh, it's because I haven't upgraded Zeta correctly. Yeah, so if you get some problems, just always specify your Python version. Like here, we specifying the exact Python version, and that should fix it. So the only bottleneck that I really think exists is like taking this from 4 dimensions into 3 dimensions so it could be concatenated with the text. So in the meantime of this, let me give you like a breakdown of this flow. Okay. So we have an image. We have some image, right? Tube. So the flow of this is basically I don't like this word. So we have an image and we're going to pass that into a vision transformer. So images are 4-dimensional tensors in PyTorch. So what we're going to do is we are going to map this image, we're going to put that as an input into a vision transformer model, which is essentially just a list of, well, first it's just a transformer, but it's handling images. So within this is just layers of transformer blocks, just stacked like that. And so that's basically just a transformer, but the thing is it's patching this. That is like, before we even get to the image, what we're going to do is we're going to take this image and we're going to patch it. That is like, we're going to create we're going to patch the image and essentially just create like different rows and stuff. So we're going to segment the image so the model can learn the image. And then after that, it'll be flattened. So this can actually, because you have to remember, in tensor manipulation, you have to have the exact same size tensor. If you do not, like, so text, image tensors are different than text tensors because they're a different shape. So like an image is batch height, width. Text is batch, sequence length, and dimension. And so images are 4-dimensional, text is 3-dimensional. Let's try running this. So here we're going to patch, and then here we're going to flatten. So this will be a 3-dimensional tensor here. And then this will be the input into the vision transformer. And so the vision transformer is going to output a classification in text, which is going to be the way Lucid Rains does it is it could be like 2-dimensional or just 3-dimensional representing text, which is batch and classes, or you could do batch, sequence length, and dimension. And so this is like the output is going to be like there's a certain classes for the objects. That is, you're taking an image and you're trying to classify the image with objects, right? And so we're going to set like the number of classes here is sort of like the number of objects in the model. So like, let's say we're training a vision sensor. Let's say we're training this model for like facial recognition. The number of classes would be the number of faces. Or it really depends on what task you're training yours on. But in the data set, there should be multiple classes. So we're about to run this again, see what happens. This is a constant, like, this is, yeah, okay. So here we have a, I don't know why this isn't working. Yeah, quick learn arm is not working here. So we're gonna turn that off, and again, don't expect anything to ever work. Expect it to not work, and then it'll work. So let's see, print the shape of this. So there's an error now with the shape. We need to debug this and see where the error is at. You see? So this is the error. So what we're going to do here is we're going to use the infamous INOPS library, and we're going to essentially reduce the shape of the tensor to a shape that is compatible with the attention mechanism. Let's run that and see what happens. So vision transformers are very useful. At the present moment, they are the best vision AI models. They're used in everything from autonomous cars to security cameras to diffusion models. Basically, every single application that involves vision for AIs, vision transformers are handling very well. So let's see the shape. So the shape here is batch height width So here what we're doing is reducing the size of the tensor so it's compatible with the transformer network. Let's see if that works. It worked. Oh, nice. Yeah, so it's working. The output size is exactly how it should be. We're patching the image correctly. We're applying the layers of the transformer. We're normalizing it, and we're also applying the output head. So no one actually taught me this, And it's very hard to find this out, but what an output head is like a head. When someone talks about a head, machine learning, they're talking about a component of the model that is actually doing the predicting. That is, like, this is the final layer. This is actually doing the prediction, seeing what the image is. So this is a we're just applying a mean. We're applying this identity function, and then we're applying a layer normalization, and we're we're projecting the outputs of the attention and the transformer blocks and from dimension to number of classes. So we're compacting the representation of the model. And so this right here is a fully built vision transformer that you can use for facial recognition, security, and a vast array of infinite use cases. So, as I said, these are the definitive best vision models currently available. There's a lot of papers on this, and I learned how to create vision models from Lucid Rains. He has a massive repo with like what is it, like hundreds of ViTs or something. It's insane. So yeah, ViTs are really good. I still think we need to optimize on the model architecture. So here's another example of the diagram I try to show you. So basically, a ViT is image, patch, flatten, transformer, out. That's pretty much it. So this is another visualization for this, but we're not using sequence pooling or an encoder. We're using a decoder. So there's been a lot of vision transformer literature, many different model architectures. The one I'm showcasing to you right now is among the simplest implementation of a ViT that you could possibly get. Let's organize this code a little bit. Nice. So yeah, that's Spectra. Now the next step after this would be finding a data set. Let's find a facial recognition data set or something. Yeah, so here this is an example of a data set that we would use for this. I'm gonna save this actually. This looks like a pretty good data set. So this is also outputting the size of like where the faces are in the frame of the picture. Let's see if there's any other data sets. Yeah, so for ViTs we need an image and we need text as well. So we need the image representation. We also need text. But my connection isn't that good. Let's see if Kaggle has it. Yeah, this is too complicated. Yeah, so I guess we'll find the dataset and train this model in the next video. Stay tuned. Let me know if this was easy to understand, or if there's any way I can improve this. Yeah, basically what a vision transformer is, it is a transformer model that has been adapted just for image processing. And that is, we're taking an image, patching it, and making it the same shape as text. So we're representing an image in the latent space as the same shape as text, so a vision transformer can understand it. And then ultimately give us a classification as for, like, what is the image? Is it a person? Is it what? You define that. This is the code. And yeah, let me know what you think, and let's keep creating more models. If you want to join the Agora Discord, we've created more than 400 models in the past 10 months, and we open source all research AI models. So if you like a research paper and there's no code for it or model, we'll help you open source it. And we could also give you GPU clusters if you want to train a specific model. And yeah, that's it for this video. Stay in tune. We have a lot more tutorials coming up, and yeah, I haven't made videos like this, so please don't wreck me in the comments for being a noob. But yeah, thanks for your time, and I hope you learned something.